So I'll start.
Yeah, please go ahead.
So essentially, what we'll be doing is something on the Poncelet point, and I'll present a result on some concyclic centroids. Okay. So Poncelet point is defined for a quadrangle, which means 4 points. We'll call them A, B, C, and P. The Poncelet point of ABCP we'll call it Z, is common to the 9-point circles of BPC, CPA, and PAB, and of course ABC. So the proof is just angle chasing. In general, all of the results in this lecture will be proved from angle chasing only. So I'll just prove that the circumcircles fit. I've marked the midpoints in the diagram. So let's say Z equals intersection of the circumcircle of D prime E prime F and circumcircle of D prime E F prime. So it's the intersection of circumcircles of these two triangles. And I'm not drawing Z in the picture because it might get messy. So anyway, I'll show that from this Z belongs to the circumcircle of DEF. And similarly, you can show that this Z belongs to the circumcircle of DE prime F prime. So it's just angle chasing. So we need to show that angle FDE equals angle FZE. For this, I'll split. So I'll start with this FZE. And split this into FZD prime plus angle D prime ZE. Now again, from concyclicity, you can get FZD prime is equal to FE prime D prime plus angle D prime ZE equals to D prime F prime E. So now we can use midpoint theorem. So basically F E prime D prime is this angle, which equals this angle, and D prime F E prime is this angle, which equals this angle. So there are some equals angle FAE, which is the same as FDE, again from midpoint theorem. Does this proof make sense? And of course, directed angle, so some issues. I'll write that down. Minus FA minus angle PAE. This equals minus angle PAC, which equals angle FDE. Yeah, so the 9-point circles of 1, 4 triangles have a common point. It's called the Poncelet point of ABCP. Any questions so far? Hello? No? Okay. I'll just go ahead then. So from the Poncelet point, we can define something called the antigonal conjugate of P. So P dash, the antigonal conjugate, is the reflection of P over Z. Um, so okay, this definition doesn't seem to do much as of now, but okay, there are some nice angle conditions with P prime, which is precisely BP prime C. Okay, again I'm using directed angles, like mod 180 everywhere. BP prime C equals angle BPC. Oh, sorry, plus angle BPC equals 0. Again, similar results. Etc. AP prime B plus APB equals 0. So basically what this is you have ABC. Let's say P is a point somewhere here. So what happens is if you kind of reflect P around BC, so let's say PA, this angle condition will tell you that B, PA, C, P prime concyclic. How do you show that from the definition? Anybody? Uh, given. So the thing is, Z lies on 9-point circle of BPC. So let's say this is the projection of P. And the thing is, if you scale the 9-point circle of BPC about P by a factor of 2, it passes through B, C, and the reflection of P about the foot of altitude, which is PA. And the thing is, 9-point circle passes through Z, so the scale of the 9-point circle will pass through P prime. So that would mean that B, PA, C, P prime are concyclic, which will give the first angle condition. Similarly, you can derive the other two. Now you can notice that these angle conditions will actually define P prime. So basically, the locus of P prime for which first condition is satisfied is a circle, second one is satisfied as a circle, third one is satisfied as a circle. So there will be a unique P prime satisfying all three angle conditions, and that is called the Antigonal conjugate of P. So I'll give you an exercise. Antigonal conjugate is the inverse of isogonal conjugate of the inverse of isogonal conjugate of P. So let's say P prime. Again, this looks scary, but proof is just angle chasing. So okay, maybe I'll give you hints. P comma Q are okay. By the way, inverse is with respect to circumcircle of ABC. So P and Q are isogonal if and only if angle BPC plus angle BQC equal to angle BAC. Similarly, angle CPA plus angle CQA equals angle CBA. And the other condition is APB plus angle AQB equals angle ACB. And then there's another condition, say Q star are inverses if and only if angle BQC plus angle BQ star C equals 2 times angle BAC, etc. I'm not writing the other two. Yeah, using these two, we can do this exercise. Okay, well, so we are going to a small digression. Fermat point. Again, so let ABC be a triangle. And a point F satisfying. Okay, I'm assuming ABC is acute. So a point F satisfying 120, 120, 120 here. It's called the first Fermat point. The second Fermat point is a point which satisfies 60, 60, 120 condition. So maybe I'll define it properly. So ABC is a triangle. You can erect equilateral triangles outside. So this one, this one. Yeah. You erect equilateral triangles outside and say call it DEF. And you take the common point of the circles BCD. BCD. That's that. Yeah, it's easy to show that these circles are concurrent. And the point of concurrence of this is called the first Fermat point. Similarly, if you erect the equilateral triangles the other way, that is, I erect them this way, call that D prime, call this D prime, F prime. So the common point of circles be F prime A, C D prime B, C prime B, C D prime C, sorry, and A D prime C. These three circles have a common point called the second Fermat point. F2. Exercise F1 and F2 are Antigonal conjugates. Yeah, okay. Next thing is, let's go back to our Poncelet point A, B, C. Let's say P. We will show that the Poncelet point Z of ABCP lies on the pedal circle of P. Pedal circle is this circle to feet of perpendiculars. So let's DEF. We'll denote the midpoints of AB and AC by, let's say, F prime, E prime. Midpoint of AC by D prime. And so we wanted to show that angle FZE equals angle FDE. And this would imply that Z lies on the pedal circle. So yeah, you can split FDE into, well, sorry, FDE. Angle FDE equals angle FDP plus
What is P
angle
then you say?
PDE. Huh? What is?
What is PP?
P is any point. Yeah?
Okay, yeah, cool.
Hello. Yeah. P is any point. Okay, actually,
Yeah, yeah.
P should not be the orthocenter of ABC. That is because the Poncelet point will not be well defined. Poncelet point we defined as the concurrence point of 9-point circles of ABC, APB, BPC, and CPA. But the issue is when T is the orthocenter, all these 9-point circles are the same. So Z is not well defined in that case. So I'll just assume P is not the orthocenter. Okay, and all fine.
Yeah, yeah.
Okay, so now again angle chasing. FDP equals angle FBP. Yes, and PDE equals angle PCE. Now you can, okay, I'll just draw it. I'll do one side. So you have this angle equals this angle. We can use midpoint theorem and shift this angle to this angle. So that's FBP equals F F prime D prime. And similarly, PCE equals PCE equals D prime E prime A or D prime E prime E. I'll just draw it here. And say this angle equals this angle. Again, midpoint theorem. Okay, so now we'll use the concyclicity of 9-point circles. We know that F, F prime and D prime lie on the 9-point circle of APB. So that means F, F prime, D prime, Z concyclic. Similarly, E, E prime, D prime, Z concyclic. Okay, so F, F prime, D will go to angle F, Z, D prime. And this D prime, E, E prime will go to angle D prime, Z, E. And these two will add up to angle F, Z, E. So that means Z lies on the 9-point circle. I mean pedal circle of P. Okay. So here's an interesting and strange corollary. Pedal circle of P intersects 9-point circle of ABC. Okay. So in general, there will be two intersection points of two circles if they intersect. Yes. So okay, I'll ask you a question. So, so let ZP be the first intersection. ZP be the Poncelet point of ABCP. What is the other intersection? What is the other intersection of 9-point circle of ABC and pedal circle? Yeah, it's a question. Any answers? Am I audible or fine?
Yeah, yeah.
Okay, so any answers or any guesses at least? So the thing is, this pedal circle of P will be the same as the pedal circle of Q for some other Q, right? What is this Q?
The isogonal conjugate.
Yeah, it's the isogonal conjugate of P. So what do you think the second intersection of 9-point circle of ABC and the pedal circle of P corresponds to? any cases. Okay, so this thing is the Poncelet point of ABCP. Yeah, someone was saying something.
Other Poncelet of ABCQ.
Yeah. So if you say Q is the isogonal conjugate of P, the other intersection is. So there are some details missing in this, but okay. So now something interesting. Yes, what happens when pedal circle touches 9-point circle? So if it touches, that means the Poncelet point of ABCP and the Poncelet point of ABCQ are the same, right? So actually, you can kind of see Feuerbach's theorem from this, because okay, maybe I'll do it sometime later in this class only. This requires some more stuff. Anyway, so here's the thing: if P is equal to in center I of ABC, then Poncelet point of ABCI is the Feuerbach point. Do you see why? Okay, I'll tell you. It lies on the 9-point circle of ABC and it lies on the pedal circle of I, which is the in circle. And since there's only 1 point in common between these two, uh, that must be the Poncelet point. Okay. Okay, next. We'll do something about isogonal conjugate of a point and a circle. Let's say you have a circle. Yes. Circle A, B, C. Okay, and let's take a point P here. So, do you know the fact that the isogonal conjugate of P with respect to ABC is the point at infinity? Is a point at infinity. Uh, no. Okay, fine. I'll change location of P. Let's say here. So I'll give you a stronger result. Isogonal conjugate of P is the point at infinity perpendicular to Simpson line of P. Okay, so I'll give you a short proof of this. So basically, I'm using some fact about the Simpson line. Sorry. So let's call this projection A sub P. Projection, not projection. Sorry. The perpendicular from P to BC intersects the circumcircular line A sub P. Then I'm going to use the fact that AAP is parallel to Simpson line. Okay, and let's consider the angle bisector of ABC. So how we construct the isogonal conjugate of P is you take line AP, reflect it about the angle bisector. Similarly, you take BP, reflect it about the angle bisector of B and so on. So what I'll do is let this intersection be P prime. Now these two are symmetric, and we know that like how do I say this? Okay, you can say that PP prime is parallel to BC, right? Yeah, okay, I'll give that as an exercise only. Exercise P prime is parallel to BC. Again, it's just simple angle chase. So if P prime is parallel to BC, that means this angle is 90 because this angle was 90. And if this angle is 90, then angle P prime AP is equal to 90, which implies AP prime is perpendicular to Simpson line of P. Okay, so similarly, you can do the same thing with B and say that the reflection of BP over the angle bisector is perpendicular to the Simpson line of P. And similarly for C. So these three parallel lines will intersect at a point in infinity. I'm not drawing the one C. So that is the isogonal conjugate of P. Okay. Any questions so far? Okay, then I'll proceed. I'm going to use one fact whose proof is algebraic. Isogonal conjugate of a line is a circumconic. Circumconic means a conic passing through all three vertices of ABC. And the other fact is isogonal conjugate of circumconic is a line. So again, I'm not considering degenerate cases when the line passes through the vertices. But in general, if you take some line like A, B, C, and a line, let's say like this, maybe like this. So you take a point on this line, take the isogonal conjugate, and move this point along this line, and you consider the images of the isogonal, like conjugate of P, and you will get a circumconic. Well, at least you can see that it passes through ABC because when P approaches this point, the isogonal conjugate should approach the point B. It's called this E. And when P approaches F, the isogonal conjugate approaches C. When P approaches D, isogonal conjugate approaches A. So this thing without proof. Okay, then so some observations. A, B, C. And the thing is, the circumconic can be an ellipse. If the circumconic is an ellipse, then it doesn't contain any points at infinity. That means the isogonal conjugate of this ellipse, which is a line, should not intersect the circumcircle of ABC because every point at infinity has an isogonal conjugate on the circle and every point on the circle has a conjugate at infinity. Okay, and next is hyperbola has 2 points at infinity. At infinity, no point at infinity. Hyperbola has 2 points at infinity, which means that the isogonal conjugate of hyperbola, which is a line, must intersect the circumcircle at 2 points. Okay. And the third thing is a parabola. Parabola has 1 point at infinity. If it has 1 point, what does that tell about the isogonal conjugate of the parabola? That's a line. The thing is, every time a line intersects the circumcircle, that point will have an infinity. That point will correspond to a point at infinity on the isogonal conjugate. So if the parabola has if a parabola is the circumconic in consideration, it has only 1 point at infinity, which means the isogonal conjugate must touch the circumcircle. So basically, some line like this. There's only 1 point here, and the isogonal conjugate of this will correspond to the point at infinity of the parabola. Okay then. Do some result on rectangular hyperbolas. Theorem. Let H be a circumconic of ABC. Um, Ortho-center of ABC is H. And show that H is rectangular hyperbola if and only if H contains orthocenter. Okay, does everyone know what a rectangular hyperbola is? If you don't know, just speak up. Anyway, rectangular hyperbola is just something like this with perpendicular asymptotes. Diagram, but okay. When the asymptotes of the hyperbola are perpendicular, it's a rectangular hyperbola. So these perpendiculars these perpendiculars will correspond to the point at infinity on the hyperbola. Okay. So here's the nice thing. Proof. So assume H is rectangular. Since H is a hyperbola, the isogonal conjugate L of H intersects the circumcircle of ABC at 2 points, let's say X and Y. So the good thing is the points X and Y will correspond to the infinity points here. So I'll call this X star and Y star as the infinity points on the hyperbola. So here's X star, Y star. And the thing is, we know X star lies on a line which is like X star is the point at infinity along the perpendicular to the Simpson line. So that's what I did here. Similarly, Y star is on the infinity perpendicular to Simpson line of Y. So if the asymptotes of H are perpendicular, that would mean that Simpson lines of X and Y are perpendicular. Now, when does this happen? And there's a nice result for angle between Simpson line of 2 points. Yeah, when does this happen? Any?
They're antipodes.
Yeah, when they are antipodes. So when they are antipodes, so I can actually put if and only if. Okay, so but okay, maybe I'll make it clearer. If they are antipodes, XY or rather L contains the circumcenter O, right? And now isogonal conjugate of O is the orthocenter. So that would imply H contains. Now going back is the same thing. Since we are assuming H is a hyperbola, or rather, let's say H is a circumconic. Containing H. Then let's call the isogonal conjugate L. L contains the circumcenter O. So if L contains O, then L intersection circumcircle will have two antipodes X and Y, and these antipodes will have perpendicular Simpson line, which implies X star and Y star, the isogonal conjugates of X and Y, are perpendicular, are along perpendicular directions. Now, since L is intersecting the circumcircle at 2 points, the circumconic is a hyperbola, and these 2 points will correspond to the direction of asymptotes. So, asymptotes are perpendicular, which means the hyperbola is rectangular. So what this says is just hyperbola is rectangular if and only if it contains the orthocenter of ABC. So we'll, we'll call this system of 4 points where one of them is the orthocenter of the other three. So let's check which is there. We'll call A, B, C, H as an orthocentric quadruple. Okay, so the thing is hyperbola is rectangular if and only if it contains an orthocentric quadruple. Okay, so here's an interpretation of this. You take a rectangular hyperbola and you take two cards on this. Let's say this one, first card, and this one, second card, so that they are perpendicular. If they are perpendicular and the hyperbola is rectangular, this interpretation says that these 4 points form an orthocentric quadruple. So A, B, C, H. Particularly, H is the orthocenter of ABC. Yeah, any questions so far? Hello? No? Okay, I'll proceed. Now, let's look at, okay, one more thing. The center of a conic is the pole of the line at infinity. Again, this is a standard result. You can use a projective transformation to prove it, or rather, affine transformation. Okay, so I'm not proving this. Think about it. Basically, for a circle, the pole of the line at infinity is the center. Now we'll look at a nice result. Suppose let's call this parallel. Let ABCD be a parallelogram, and let C or C conic through ABCD. Then the center of C is point O. Okay, so can someone give me a short proof of this? Should I draw the conic? I'll draw it, let's see. Again, the only fact I'm using is the center is the pole of the line at infinity, and this is a parallelogram, so that should give you enough hints. Okay, no replies. I'll go ahead. Proof is just Broca's theorem on ABCD. So the intersection of AD and BC is one point at infinity. The intersection of AB and CD is the other point is some other point at infinity. So the pole of the intersection of diagonals is the line at polar of the point of intersection of AC and BD, that is O, is the line at infinity, which means O is the center. Okay, so that's a nice result to remember. Anyway, let ABC be a triangle. I should draw the circumcircle first. Yeah, circumcircle A, B, C. And let's say H is the orthocenter of ABC. Now consider some rectangular hyperbola through ABC and H. Let's say it looks like this. Not a good diagram, but okay. And so the thing is, any two conics in general will intersect at 4 points. Okay, maximum 4 points. Since these two conics, like conic, the second conic I'm talking of here is the circumcircle of ABC. These two conics intersect at ABC. There's a fourth point of intersection. Let's call it D. So we want to look at the center of this conic. Let's call this H. Okay, the thing is, if D is on the conic, then the orthocenter of DBC is also on the conic. Let's call it D prime. This is because of the result on rectangular hyperbolas. So you take this triangle, orthocenter will also lie on the conic H. So let's say it's here, D prime. Okay, so it's a famous or very well known result that AH D prime D is a parallelogram. In fact, you can remove the hyperbola from the picture to visualize this. So let's take a cyclic quadrilateral ABCD, or the center of ABC is, let's say, H. The orthocenter of DBC is, let's say, D prime. So if ABCD is cyclic, then I'm saying that this quadrilateral is a parallelogram. Again, proof is not hard. I'll give that as an exercise to you. Okay, so from this result, which you just did, center of the conic is the center of the parallelogram. We have a nice result that the center of this circumconic H is the midpoint of DH. Yeah, so let's call this Z. The center of the conic is the midpoint of DH. And the good thing is the midpoint of DH lies on the 9-point circle of ABC. That is because scaling the 9-point circle of ABC, it's centered at H with the ratio 2 will send it to the circumcircle of ABC. Maybe I'll draw a diagram for that also. Let's say okay, let's say H. The 9-point circle of ABC passes through D, E, and F, which are the bit of altitudes. Now, if you scale this by 2, D goes to a reflection of H in BC, E goes to a reflection of H in CA, F goes to a reflection of H in AB. So the 9-point circle will go to circumcircle. So basically, if you remove D from the picture and the circumcircle from the picture now, what happens is we have this result. Consider, uh, rectangular hyperbola H through ABC as center on the 9-point circle. Okay, so now here's here's the interesting thing. Now we'll add P into the picture. And I'm assuming P is not the orthocenter, obviously. So consider the rectangular hyperbola through ABCP. There exists one rectangular hyperbola through ABCP, which is not hard to see. Take the orthocenter H and consider the hyperbola through ABPCH. Okay, so 5 points define a conic, and in this case, yeah, so ABCP has a rectangular hyperbola, H passing through one of them. So we'll call that circumrectangular hyperbola. Circumrectangular hyperbola H of ABCP. Now here's the thing. Let Z be the center of the hyperbola. From this theorem, Z lies on 9-point circle of ABC. But then if you remove A, PBC is also a triangle inscribed into H. So Z will also belong to 9-point circle of PBC. It also belongs to 9-point circle of PCA. And it also belongs to 9-point circle of PB. So this means that Z is the Poncelet point of ABCP. Okay, it's a cute result. That Poncelet point is the center of the circumrectangular hyperbola to the 4 points. Okay, so now we can kind of prove result. Fontenay's theorem. I don't remember which Fontenay theorem this is. Fontenay's theorem. So what it says is pedal circle of P touches 9-point circle of ABC if and only if O, P, Q are collinear, and Q is the isogonal conjugate of P. Again, so okay, this is not hard to prove. Say okay. As first assume pedal circle touches the 9-point circle at ZP. Then the isogonal, I mean, what did I say? No. ZP is center of circumrectangular hyperbola through ABCP, and ZQ is uh, okay, so ZP lies on pedal circle of P, ZQ lies on the same circle because they have same pedal circle. If the pedal circle touches the 9-point circle, that means ZP equals ZQ, implies the hyperbola is the same. That means A, B, C, P, Q have okay, hyperbola, rectangular hyperbola passes through A, B, C, P, Q. If that happens, if you take the isogonal conjugate of that rectangular hyperbola, we will get a line, and that line passes through the circumcenter of ABC. Wait, I'll write that down. ABC, PQ, conic through ABCPQ is rectangular hyperbola. So if you take the isogonal conjugate of this conic, you will get a line L passing through the circumcenter because this rectangular hyperbola contains the orthocenter of ABC. Now L also contains P because Q is on the hyperbola, and L contains Q because P is on the hyperbola. So ZP equals ZQ implies OPQ are collinear. Now similarly you can go the other way. OPQ are collinear, then the isogonal conjugates are isogonal conjugate of that line OPQ is circumrectangular hyperbola, which would mean the Poncelet point of ABCP and ABCQ are same. And from that, you can say that the 9-point circle of ABC touches the pedal circle of P. Yeah. So I don't remember which Fontenay theorem this is. There are 3 Fontenay theorems. There's a nice article in Mathematical Reflections. I urge you to read that. Now we'll look at some nice configuration. It's very interesting actually. So take ABC triangle. And you take a point P here somewhere. Of course, not equals to the orthocenter of ABC. Let H be the orthocenter of ABC. Let's say H is there. And let say HC is the orthocenter of HB is the orthocenter of BPC is AB. Okay, you just take the orthocenter of these 3 smaller triangles. So let's say orthocenter of APB is HC, which is here. On the orthocenter of BPC is somewhere there, HA. Yeah, so this configuration gives like really nice properties. So for example, I'll give that as exercise. Circumcircle of AHBHC, circumcircle of BHCHA, and circumcircle of CHAHB are concurrent. Yeah, you can try that yourself. Maybe I'll give you a hint later. Okay, now we'll come to the main theorem for this thing. Cyclic centroids. So centroids G, G, GB, GC of triangle ABC, triangle AHBHC, triangle BHCHA, and triangle CHAHB are concyclic. So this is a remarkable result because in general having concyclic centroids is rare. Centroids are usually not associated with angles and circles. Okay, so any questions until now? I'll move on to the proof of this theorem. No questions. We'll do the proof. So I have a diagram from GeoGebra here. Okay, so okay, so uh, I'll just write down what G is. G is ABC centroid. G is AHBHC centroid. GB is AHBHC centroid. And GC is the centroid of CHAHB. So, okay, first thing, this line AG. Okay, so we'll take the midpoint of HBHC, let's call it M, and the midpoint of BC, let's call it N. Okay, so HC is the orthocenter of BPC, so BHC is perpendicular to AP. Similarly, CHB is perpendicular to AP, which implies BHC parallel to CHB. You can see that in the diagram here. These two lines are parallel. If these two lines are parallel, these four points form a trapezoid, and so the midpoints of the diagonals of this trapezoid, they will also form a line which is parallel to them. So that basically means parallel to MN. Now the nice thing is here A, G sub A and M are collinear, and the ratio is like 2/3. Similarly, A, G, N are collinear. I'll erase these two lines, but yeah, basically what I'm saying is GGA is parallel to MN. Look at homotheity ratio 2/3. Okay, so that means GGA is perpendicular to AP. Similarly, GGB is perpendicular to BP, and GGC is perpendicular to CP. So now these will give angle conditions. Angle GGB GGC equals angle BBC. I'll draw that in the diagram here. This angle equals sin. Okay. So now we'll look at GAGB and the other lines. So, okay, let's go to this figure. Here I've marked the midpoints of AHB and BHA. So, G is the orthocentroid of GB is centroid of BHA. So again, using vectors or maybe even simple angle, not angle chase, simple length chasing, you can show that. Let's say this is the midpoint. Let's call this M. Point of this CHSN. The point of AHC is, let's say, D, and this is E. Let's say. So you can show that EM is parallel to GAGB. GM is parallel to GAGB. Again, this is just This is easy. Now here's the thing. Again from Brocard's theorem, we can say one nice result about trapezoid inscribed in a conic. So let's say this is a conic, a trapezoid ABCD, and let C be a conic. C is a conic through ABCD. So from Brocard's theorem, and let's say the point at infinity, let's call that P infinity, and let's call these two xy. Polar of P infinity with respect to C is xy, and it's a famous result with trapezoids that this line xy is the line through midpoints of AB and CD. Okay, so the polar of P infinity will pass through the center of C. So that means xy passes through the center of C, or in other words, if you take a conic and you take two parallel chords and you take the midpoints and join them, this line will pass through the center of the conic. Okay, so that would mean that EM and DN pass through the center of the conic, which I marked as Z. Oh, and here the conic is the conic through ABC, PH, which also passes through HA, HB, and HC because it's rectangular. Yeah, so now Z is the Poncelet point of ABCP. So that would mean it lies on the 9 point. Oh, so, okay, Z is the Poncelet point of ABCP. It's also the Poncelet point of HABCP because they have the same circumrectangular hyperbola passing through. And the circumrectangular hyperbola will define the Poncelet point because Poncelet point is the center of that hyperbola. Yeah, anyway, that means Z lies on 9-point circle of HABC. The 9-point circle of HABC is the circle through these 3 points, M, N, and this point. So that will give us some angle condition on Z, that is MZN equals, let's call this, I don't know, A prime equals angle M A prime N, which by midpoint theorem is angle minus of angle M H A N. And since HA is the orthocenter of BPC, you can see that this angle is the same as this angle mod 180. I'll erase these two. This is equal to angle BPC. So we have this nice result, and the thing is angle MZN equals the angle between EM and DN, which equals the angle between GB GA and angle between GCGA. I'll erase this figure also. Also, this is what I've shown. EM is parallel to GAGB. These two lines are parallel. Similarly, these two lines are parallel. So that is equal to angle GB GAGC and MZN equals angle BPC. So previously what we found was this result. Combining these two, what we get is angle GBGAGC equals angle which implies GA, GB, GC and G concyclic. Also erase this result. Yeah. So there are some nice results I also skipped while doing this session because it's outside the scope, I think. Rather, I have not encountered some easy proofs. So one Poncelet, okay, point of ABCP lies on CVN circle of P. So CVN circle of P means circle through CVN triangle. Now this is a result I skipped. It's probably harder to prove. Okay, and maybe some further reading. So there's one article by Van Poncelet and applications. There's an awesome math article, I don't remember who wrote it. It was on the Fontenay theorems. And there's an AOPS post. I just linked in this article. You can have a look at it. Yeah, okay. Thanks for attending. I think I should stop sharing the screen. Yeah, where is the